In this video we present our IROS 2023 paper on exploring social motion latent space and human awareness for effective robot navigation in crowded environments. Social robot navigation is a crucial aspect of social robot applications. Robots moving among humans must execute safe, smooth, legible and socially compliant actions. We propose to use a social motion latent space of a pre-trained multimodal human motion trajectory predictor which leads to smooth, legible, anticipatory, and continuous controls. We introduce human awareness towards the robot into the social robot navigation framework. Aware humans may yield to the robot. Our policy learns to leverage the positive interaction from the aware humans, allowing the robot to deviate less from its path, resulting in efficient navigation. We are superior to relevant previous methods across metrics, including generating continuous controls, despite not being trained on it. Social robot navigation requires the robot to navigate amongst humans in a safe and socially compliant manner, respecting their personal space. The robot is required to navigate in the environment while avoiding collisions with humans. In a typical crowd, humans can be both aware of the robot or are unaware of the robot when they are preoccupied with some other work or when the robot is not in the view of human. Aware humans tend to yield to the robot, whereas unaware humans tend to continue their trajectory course and do not yield to the robot. We show humans aware of robot as green disks and unaware humans with purple disk. Robot is depicted as a black disk. Our novel network architecture consists of two modules, namely, controller and a social motion latent space parameter predictor. The latter is pre-trained and kept frozen. The observation consists of human and robot motion and geometric parameters. It also consists of our newly introduced human awareness. We use pre-trained social VAE as the social motion latent space parameter predictor. Social VAE takes the target humans and its neighbors' historical motion parameters as input. The encoder then produces a social motion latent space based on the input. This latent space can be sampled and decoded to produce multimodal trajectory predictions. In our case, we pass the historical motion parameters of the robot and its human neighbors to the encoder of social V, which produces social motion latent space parameters. This latent space can be sampled and decoded to produce multiple velocity controls. Since the pre-trained social motion trajectory predictor is trained on just human motion data and it does not have the concept of goal. Due to this, the nature of the social motion latent space is to produce multimodal actions which are only social in nature but are not goal-driven, which is required. This is handled by our controller module. Robot and human state at current time step is passed to the controller module as input, which is passed through the robot-human attention block. The output of this is combined with the latent space parameters predicted by the encoder of the social motion latent space predictor. This then produces a learnable perturbation. The social motion latent space is sampled by combining the social motion latent space parameters with the learned perturbation. The sample is then passed through the decoder of the social trajectory forecaster to produce actions. The actions produced are velocity controls which are continuous in nature. These are then mapped to obtain the closest control in discrete action space, which are social and goal-driven. We include comparison of our model with baseline models. Our observations indicate that the trajectories generated by our method are smooth in nature. The actions taken by the robot ensures that it maintains sufficient distance and respects their personal space. We compare our model with baselines trained on continuous actions. Despite being trained on discrete actions, it produces smooth and socially aware trajectories. This is attributed to our use of continuous social motion latent space. Here we show how our policy leverages human awareness to achieve shorter trajectories. Our model can anticipate human motion by the virtue of human motion latent space. The policy attends differently to different humans based on their trajectory and awareness state. Here we show the benefits of using a social motion trajectory forecaster. We observe that our method is able to produce smoother trajectories when we include the social motion trajectory forecaster.